Dams are some of the largest structures humans have ever built. Their job? To hold back billions of tons of water. Water may look gentle, but at scale, it becomes one of the most powerful forces on Earth. At the base of a dam, water pressure can exceed 1,000 kilopascals, equal to the weight of 10 cars on every square meter. The Hoover Dam holds back Lake Mead, storing 35 billion cubic meters of water. That's more than 14 million Olympic-sized swimming pools. The Three Gorges Dam in China is even larger, holding back 39 billion cubic meters of water. Without careful design, the force of this water could crush concrete and sweep entire valleys away. So how do dams survive? It starts with foundations. A dam must be anchored to solid bedrock. Engineers drill deep into the earth, sometimes over 100 meters, to lock the dam in place. If the foundation is weak, water will seep under the structure and cause failure. That's why dams like the Hoover Dam were built in narrow canyons with strong granite walls. Gravity dams, the most common type, rely on their enormous weight to resist water pressure. Hoover Dam itself weighs about 6.6 million tons, the weight of 18 Empire State Buildings. The concrete is so thick 200 meters at the base that it can withstand the crushing force of the reservoir. Every drop of water pushes against the dam, but the structure channels that pressure safely into the ground. By spreading the load into the canyon walls and bedrock, dams redirect water's fury into stable earth. That's why even after decades, dams like Hoover and Grand Coulee remain unshaken by the water they hold. But weight alone isn't enough. Engineers also shape dams to handle water pressure efficiently. That's where the magic of arch design comes in, and why dams are as much about geometry as mass. Not all dams are just massive walls of concrete. Some are shaped with precision to use water's force against itself. Arch dams are curved, designed to transfer water pressure sideways into the canyon walls. The Hoover Dam, for example, is a gravity arch dam, both massive and curved for extra stability. The Kariba Dam in Africa is another giant arch dam. At 128 meters tall, its curve channels water pressure into solid rock. By curving upstream, the water's force is spread out like a person leaning into a wall for support. This means less concrete is needed compared to a straight wall, making arch dams more efficient. But even with perfect shape, water pressure can build to dangerous levels. That's why dams need spillways. Spillways act like safety valves, releasing excess water during floods or heavy rains. The Three Gorges Dam has 22 spillway gates, each capable of releasing over 4,000 cubic meters of water per second. That's like draining an Olympic swimming pool every quarter of a second. The Hoover Dam has both surface spillways and tunnels drilled through the canyon walls to redirect water safely downstream. Without spillways, rising water could overtop the dam, eroding it and causing catastrophic collapse. Pressure distribution is another secret. Water doesn't push equally at all levels, it increases with depth. At the surface, pressure may be small, but 100 meters below, the same water exerts crushing force. That's why dam walls are thickest at the bottom and thinner near the top. For Hoover Dam, the base is 200 meters thick, but the crest is only 14 meters. This tapering design balances strength with material efficiency, resisting pressure where it's greatest. Every part of a dam is shaped to guide water's energy safely, turning unstoppable force into controlled power. From the curvature of its walls to the hidden tunnels and spillways, dams survive because they never fight water, they work with it. Dams don't just hold back water, they also create power. Most modern dams are hydroelectric, turning falling water into electricity. The Three Gorges Dam has 34 generators, producing 22,500 megawatts, enough to power 70 million homes. The Hoover Dam generates around 2,000 megawatts, supplying electricity to Nevada, Arizona, and California. Together, hydropower dams supply about 16% of the world's total electricity. That's clean energy, created simply by letting gravity pull water downhill. But despite their strength, dams are not invincible. History has seen tragic failures. The Banqiao Dam in China failed in 1975 after extreme rainfall, releasing 700 million cubic meters of water in hours. It caused flooding that killed an estimated 170,000 people, one of the deadliest engineering disasters ever. In 1928, the St. Francis Dam in California collapsed, wiping out communities and killing 431 people. These tragedies remind engineers that safety systems, spillways, monitoring, and inspections are critical. Modern dams use sensors to detect cracks, shifts, and water seepage in real time. Drones and robotics now scan dam walls, checking for signs of stress before failure occurs. Future dams are being designed not just for power and water storage, but also for resilience. Engineers are experimenting with self-healing concrete, which uses bacteria to fill cracks automatically. Some countries are removing outdated dams to restore rivers, while others plan megadams for energy security. The Itaipu Dam in Brazil and Paraguay produces 14,000 megawatts, powering both nations for decades. As climate change brings heavier floods and longer droughts, dams will face even greater challenges. Yet they remain symbols of human engineering, giant walls standing against billions of tons of water. From ancient stone dams to today's mega projects, they prove that with design, analysis, and constant vigilance, humanity can tame rivers. The next time you see a dam, remember it's not just concrete. It's precision engineering holding back unimaginable power.